Hello, everyone. Welcome to another tinyML Talks. This is hosted by the tinyML Phoenix section. And today we have Professor Daphne Chen from Northern Arizona University, who will be talking about novel device and materials in emerging memory for neuromorphic computing. So we'd like to acknowledge our tinyML Talk strategic partners listed here on the slide, a really vibrant community of industries and companies. Additional sponsorships are available, and you can contact Olga at tinyml.org for more info. Uh, it's actually past the tinyML Summit, but that doesn't mean you can't still participate. Uh, we did have a in-person event, March 20 to 30. It was very successful in-person event post the pandemic, and we're really excited about all the interest that we received. The presentations are available on www.tinyml.org, and the videos will be made available on our YouTube channel, as well as there was a research symposium on the 28th. More sponsorships are available for tinyML. You can contact sponsorships at tinyml.org for more information. Also, we're growing our tinyML communities. We have about 9,000 members in 45 groups across 35 countries. It's really quite amazing to see the growth of this community, as well as in LinkedIn, about 2.7K members and 6.1K followers. Also, please subscribe to our tinyML YouTube channel for updates and notifications, including this talk recorded here today. We have over 6.4K subscribers with over 192,000 views, so definitely a great resource for you as you plug into the tinyML community. Just to advertise for the next talk is Tuesday, April 12th. Professor Devastria will be talking about machine learning, supporting ecology, supporting machine learning. That webcast will start at 8 a.m. Pacific time. And if you're interested in presenting, please contact talks@tinyml.org. So with that, it's my great pleasure to introduce Professor Ying-Chen Daphne Chen from Northern Arizona University. She received her PhD degree in electrical and computer engineering at UT Austin in 2019 and a BS and MS degree from National Chiao Tung University in Taiwan. She's currently an assistant professor in the School of Informatics, Computing, Cyber Systems, the Department of Electrical Engineering at NAU. She also is an affiliate professor in the Materials Research and Diversity Center. Before NAU, she worked at Micron Technology on emerging memory systems. She has a broad range of research interests in emerging electronics, memory devices, and energy-efficient integrated systems, and has co-authored several publications. She's also the recipient of the Sandia National Laboratory Research Award in 2019 and the EECS Rising Stars in 2017. So let me welcome Daphne, and looking forward to hearing her talk about novel device and materials in emerging memory for neuromorphic computing.
Sounds good. Thank you, Sharon, for this great introduction. So I really appreciate that. And thanks again for tinyML for inviting me, for giving this, sharing our result and giving this talk. So my name is Daphne Chen, and today I'm going to talk about the novel devices and materials in emergent memories for the neuromorphic computing. And there you go. So let's see. This is today slide outline. First of all, I will introduce why emergent memory and why is that important for the next generation AI applications and also neuromorphic computings. And this will be expected as much more leaning on the device and material area, trying to do the hardware for the AI applications. And second section, I will talk about result and discussions, which include the novel access devices selector, and one very unique devices we developed is called Selector-less Resistive access memory. And I'm gonna also talk about radiation effects on ruthenium-based RRAM devices, which is CMOS backend offline compatible. And the fourth topics will be the tungsten oxide-based memory with the transparency that which can be a possible candidate to integrate with the optical-driven silicon photonics interconnect for the the future embedded memory. And then I will talk about the thermal stability on a volatile memory based on neuromorphic computing, and how does the thermal energy and dynamics affecting the training and inference. Then I will conclude my talk. So why does memory nowadays become more and more important? So the answer can be very short, is that memory is inevitable, like it's very essential for the every kind of chip manufacturing, from network to transportation, automotive, and high performance computing. So supercomputer, space station, mobile devices like a smartphone, portable healthcare devices, and storage class memory, which is more conventional non-volatile storage class memory, like memory card, hard drive, flash drive, and so on and so forth. And also, there's a lot of memory components that in embedded microcontroller units in our daily life, such as SIM card, credit card, so on and so forth. So, but now memory has become more and more important than before, which is only purely for the storage. Now we are trying to utilize the memory for enhance the computing performance. So I want to share one slide here, is memory hierarchy, which might be seen in a lot of talks at tinyML. So basically is that from top to bottom is from the computing unit to the storage unit. And there's many kinds of memory devices in the hardware chips, so which is SRAM, DRAM, and storage class memory, and also the non-volatile flash memory, SSD, so on and so forth. So as you can see that, so the pyramid, the top of pyramid memory has the highest speed, but it will have a limited capacities, and the bottom of pyramid will have a higher capacities, but the speed is quite slow compared to the memory unit close to the CPU. So there's a memory latency and energy overhead in this kind of memory gap, and this will become more and more significant issues as now is the data-centric computing era, and we need much more higher performance and as well as a higher storage memory. So to finding the next generation memory which can bridge up the gap and which can link in much more into the computing, such as the in-memory computing and neuromorphic computing, will be the important topic. And here I want to share some current applications for non-volatile memory. So I categorize the applications for three topics, which will be much more linking on the hardware memory. So one is storage class memory. And as we know that the current phases, the non-volatile memory, flash memory has a very good scalability in terms of using the 3D. However, it is transistor-based, and it will encounter huge issues for the charge loss in a floating gate. And the bit error rate will increase as the technological decrease, and also endurance will decrease with the scaling devices. So finding the next generation emergent non-volatile memories become more and more important to replace the flash memory to overcome this charge loss and retention issues, and to make it much more reliable for the non-volatile storage memory. So this is the first one. And second one, as I mentioned in previous slide, is that we want to realize the new computing architectures, which is can break through the memory wall, which is existing in the voluminous structures. As you can see in this slide, is that there's a lot of traffic between the process unit and memory, and which will causing a lot of latency and energy overhead. So this is what we want to propose, that using the non-volatile memory as a primitive, and we can break through this conventional computing structures. So neuromorphic computing will be one candidate, and also computing in memory, larger in memory. So I think there's, based on the from device level to system level, there's a lot of application is going on right now. And the third one will be the hardware security. So non-volatile memory is seen as a very good primitive for the hardware security. especially now there's more and more informations which is should be secured in the hardware side as well as the software primitive. So for example, the physical unclonable function, this is one of the very intrinsic and reliable hardware security primitive that we can apply for on the based on the randomness and also the intrinsic randomness of the memory devices. And also we can use in the memory devices for the true random number generator as well. So there's much more applications for the hardware security as well as the computing and the storage. And here I want to introduce a little bit about memory and memory categories. So memory can be characterized into two categories. One is volatile memory, the other is non-volatile memory, and which means that if you have your information stored and without the power supply, then the information will be lost if you don't apply the power supply in the volatile memory. But non-volatile memory is that you can retain the data for up to 10 years or even longer without the power supply. And as you see in the pyramid, the memory pyramid in the previous slide is that the volatile memory, including SRAM, DRAM, and which is very quite mature technology nowadays in the market. And then non-volatile memory, including the compact disk, hard disk drive, flash memory, and immersion memory. And as I mentioned, flash memory as a big market for the non-volatile memory now is encounter some challenges scaling. So for example, bit error rate increase need much more ECC and error correction code, and then slower speed and lower retention endurance. So we want to find the next generation immersion memory. And there is 4 candidates that could be seen as the next generation memory. And one is MRAM, magnetic random access memory, ferroelectric random access memory, FERAM, and then phase change memory, which is driven by the thermal. And then the last one will be a resistive random access memory. Depends on the filamentary structures formed in the insulator. So I will talk more about that. And before we sing that, for the mechanisms, I want to highlight that those non-volatile memory has been developed by many industry companies for such very long time. And as you can see that in the industry level, they are trying to focusing on how to using the non-volatile memory, not only for the storage, but also for the back-end offline embedded memory for much more lean on the new computing architecture. And by comparison, there's many specs that we will be much more interested in to evaluate one immersion memory. So the right-hand side of the table will be the comparison between MRAM, FERAM, PCRAM. And the reason why I'm studying the resistive random access memory, because there is some advantage of that as a candidate among those 4 immersion memory, which is it has a good non-volatility, simple structure, 2 terminal, high scalability, low cost, high speed, and low power consumptions. And we will see much more details mechanisms for that. But let me introduce what is the resistive random access memory. So the theory of this RRAM devices has been bring out by the Dr. Leon Child at UC Berkeley back to 1971. And he mentioned that if it's pinched, then it's a memristor. And memristor could be ubiquitous. So this is the butterfly curve that we can using to writing 1 and 0 and 0 and 1. And let's take a look at the structures. So the structures, as I mentioned in previous slide, it is very simple and easy to fabricate it. So for example, it has a top electrode, insulator, and bottom electrode, sandwich structures, and you apply the bias and trying to form the filament, which will giving you the conductive percolation path. So you will see this conductive filament, and you can write it as 1. And then with applying the negative bias that you will rupture the filament, which will bring the conductive filament to much more oxidized state, then this will bring it you to the high resistance state, which you can write it as 0. And the worst to mention it is that this is a reversible process. So you can write 0, 1, 1 to 0. And this is how the resistive random access memory has been operated. And as I mentioned, it is highly scalable. And then the switching gap can be narrowed down to 10 nanometer or even lower to 2 nanometer, because it's controlling the atomic level switch of the atoms. And furthermore, nowadays we are focusing on how to implement this into the high storage class memory, and which we can use in the crossbar array. So this is also the same structures that Intel and Micron was working on the 3D crosspoint. But this is all the ultimate structures that all kinds of the emergent memory devices could be going to. But before realizing this, there's a huge issues that inevitable issue we need to overcome, and which is called sneak pass current. So what is sneak pass current? Sneak pass current means that when you're trying to select one cell, for example, here is a pink cell, and you apply the bias, and then you're trying to read out or trying to write that selected cell. This is not the only path will be the current going through, but also the neighboring cell will contribute the leakage. And the more selected cell you have, then the much more severe the sneak pass current will be, causing the read arrow or write arrow. So this is inevitable problems that before we can realize the crossbar array. And the worst case that here is that if you have a selected cell under the high resistance state and your neighboring cell under the low resistance state, that this is the 1/3 reskin, then you will see that the sneak pass current going through that. This will be very leaky, contributing from your neighboring cell and causing the much more maximum effect of your sneak pass current. So how to solve that? There are many solutions has been proposed from both the academia and industry. And the most standing out solution is called 1S1M or 1T1R or 1S1R. So which means that if we want to rectify, suppress the sneak pass current from the neighboring cell, then we can integrate it one transistor, one selector, or one access devices individually right next to the memory. And there's a lot of options for this kind of selection devices. So first one is the field effect transistors, for example, TFT, CMOS, MOSFET, and then dial, and then you can using that to switch on and off for the selected devices. And then the second category will be thermal-driven transition materials. So for example, the mode insulator transition, chalcogenide materials. So this is much more sensitive to the temperature. So by changing the temperature, at certain temperature, you will change the phase of the material. So you can change the resistance, and you can have a switch on and off, trying to control the sneak pass current in the array. And then the third one will be band engineering materials. So one example here is the metal semiconductor metal structures. So we can using the band engineering knowledge that we learned from the semiconductor physics and trying to build up the Schottky dial or using the tunneling behaviors. So we can control the current to going into the memory cell or we can better control the sneak pass current from the neighboring cell. But however, this kind of approach will causing a higher overhead and fabrication complexity because as we know that the memory cell is much more smaller than the selection devices. And so this will be the trade-off if you want to optimize the scalability of your memory array. So I'm thinking is that if we can find one memory cell, which itself has an immunity towards the sneak pass current from the neighboring cell, then there will be an ultimate goal for the project that we can realize the crossbar, but we don't need to use it so much of the footprints for the transistors. And here is that we come out a solution that we're using the bilayer oxide staking and trying to fabricate that in the clean room and using the compatible fabrication that compatible to industry spec, which is using the RF sputtering oxide, titanium nitride as a bonding electrode, and then we're using the bilayer staking structures, trying to build up one single cell, which that cell will have the immunity for the self-selected, for immunity for the sneak pass current from the neighboring cell, and which means that it is self-selected. And this is the fabrication process. And let's take a look at the electrical data right here. So as I mentioned, back to old days, if we want to integrate the 1R in this crossbar array, then there will be a very severe sneak pass current. And if we're using this bilayer staking structures, we expected that tuning the dielectric constant and the ratio of the thickness, then we can have a good self-rectifying behaviors. So the right-hand side is that the black curve is the single layer structures, which is conventional RRAM devices without the self-rectifying behaviors. And the red curve is the self-rectifying selector-less RRAM. So as you can see, the curve is quite different than the conventional resistive random access memory. And let me explain this a little bit. So if you have your neighboring cell under the bias of the 1/3 voltage, and then you have the selected cell under the fully voltage, then which is the pink one, then you can realize that the current at the neighboring cell has been much more suppressed from this two green dots. So as you can see that we can still read out the information that for our selected cell, but also we can suppress the sneak pass current from the neighboring cell. So this is the first step that we are trying to realize this selector-less RRAM. And we can see that the higher nonlinearity, which is defined as the 1/3 read scheme, which is the current at the V-read divided by the current at the 1/3 V-read, will be higher here compared to the conventional single layer devices. So the next question is that how does this selector-less RRAM can be utilized into the array, and what would be the array margin and array size? So we're using the 1-bit line PWAP scheme to simulate and modulate, evaluate the overall number of all lines and also the array size with a very reasonable read margin. So as you can see, left-hand side is that the model we are using, and the right-hand side, the result turns out that the bilayer selector-less RRAM array size can go up to 10⁴ times larger than the conventional single-layer RRAM devices, which you can compare the red curve or the blue curve to the black curve. So black curve is the conventional RRAM devices. So this is very exciting result that for us to seeing that how can we utilize for this crossbar array. And next step we are thinking about is that can one single physical bit store more than one state? And can this selector-less RRAM still has this kind of multi-level cell applications? And the answer is yes. So we can modify the multi-level state with the resistive voltage. As you can see in the left-hand side, controlling different high resistance state with a different resistive voltage, which can be realized in this hafnium oxide silicon oxide staking structure. And the right-hand side is the AC pulse modulation. So we modulating the pulse height and with the fixed pulse width, and we will see the multi-level cells that we can realize to further increase the scalability of the cell. So one physical cell can store multi-level state and multi-bits. So the future path for this storage class memory, I will characterize like this. So moving from 1S1M and selector-less RRAM array for 2D, and then moving to 1T1R 3D, then vertical selector-less RRAM for 3D, and also the multi-level bits, which can be realized into 1 bit. So with that, we can have very good suppress capabilities for the neighboring cell, but also has a higher scalability with the both not using the transistor and also the multi-level bits can be stored. So this is the future point for that. And not only the silicon oxide, we are also looking into different materials because based on our mechanism understanding that we need one single high K layer and one single low K layer. And to optimize the ratio of that, then we will have a very good self-selector-less RRAM with a good nonlinearity curve right here. So to prove that theory, that we will see in 1 minute. We do try the different kind of material, which is graphite oxide here. And the measured K value is about 3.01 by using the CV measurement, then which is comparable to the silicon oxide as a very low K material. And as you can see that the blue curve is also seeing the selector-less behaviors that in this bilayer staking structures. And this is quite repeatable for the higher endurance operation as well. And so the conclusion is that we have a low K dielectric layer, and then we can using that to integrate with the high K layer and to have a good selectivity. So the thickness effect and area effect, which we study a little bit, is that we found out that the thickness has not quite significant dependency for our nonlinearity. So if you further increase the graphite oxide thickness, then actually the nonlinearity will not increase. So it is much more important that how you control the filament and how you control the ratio of your high K and low K layer. And also we study the device size area from 0.4 micrometer to 1 micrometer as a single device level study. And we found out that the nonlinearity is above 120, and which is superior record numbers of the selectivity, self-selectivity and nonlinearity with the 10% acceptable remargin. So, and also it doesn't have a device dependence. So this is one of the hints that we can have a better scalability in the near future if we want to integrate this device into the crossbar array. And reliability properties right here is that we're showing the endurance of the two different kind of staking structures, hafnium oxide, silicon oxide, hafnium oxide, graphite oxides. Then we will see the endurance, the memory window, and also endurance devices, endurance characteristics for these two kind of different devices. And then we see the nonlinearity also sustained up to 10 to the 3 seconds that under the room temperature. We are doing some thermal acceleration failure tests. And it also, I didn't include the data here. It also sustained that for the over 10 to 3 seconds under the 125 degrees C, trying to meet the industry structure, industry specs. Then I would like to take a minute to talk about the mechanism beyond that, and which is the theoretical studies that we want to understand. Why does this bilayer staking structure can give us very good nonlinearity and self-selectivity? So here is a figure that we are measuring our nonlinearity as a function of set compliance current. And set compliance current can use to optimize the self-selectivity, which is that you will see between 0.5 milliampere to 3 milliampere, there's an operation window with a very good nonlinearity. And that is the optimized point that for a certain set compliance current will give you the best nonlinearity. And then the mechanism beyond that can be divided by two. So one is the below, at the very low set compliance current, you will see the filamentary geometry has been changed with this set compliance current limit change. So you will see the filament will be grow from your negative bias area, and then will push that switching gap towards your positive bias area, and because of this oxygen vacancy movement. So we want the switching gap to locate it in locate layer, so which will giving us a higher nonlinearity. And then the second one, the second period of your set CCL control, which affecting your nonlinearity, is the temperature effect, or we call thermal effect. So once your switching gap relocated to your locate layer, then as the further temperature going up, the band gap of this insulator will be going down, dielectric will be going down, and then the K value will be going up. So as the K value going up, that based on our derivation of the Paul-Frankel emission, then your K value increase, then your nonlinearity will decrease. So this is the how the set CCL can control your nonlinearity. And we do some temperature accelerating study that's trying to prove where is the gap, where is the resistive switching gap. And we combine the set CCL effect with the temperature effects. And as you can see that with a higher set CCL will giving you much more robust filament. And for the lower CCL will giving you much more higher current drift during the same time of testing, because the filament is much more thinner and also is not as robust as a higher CCL. So with that relaxation, you will see the switching gap can be happened neutrally when you do the temperature accelerating testing, and the relaxation will happen to tell you where is the switching gap. So the temperature effect also causing the current drift as well. So the highest temperature will give you much more faster relaxation occurs. So by using this tool and combining with the experimental data into the activation energy feeding through the Arrhenius equation, then we can using this activation energy of the relaxation to as an indicator for where is the switching gap of the resistive random access memory. So by comparing these two indicators, then comparing the bilayer staking structures with as a function of set CCL, then we will find that as the highest nonlinearity is happening when your switching gap is located in silicon oxide. So this is how the indicator can be used. And we will see that this is comparable to our derivations and the CCL controlled optimized nonlinearity. And the activation energy for the silicon oxide is much lower than hafnium oxide, so which telling us that the filament relaxation rate is much more higher in silicon oxides than hafnium oxide. And this will be the indicator that if we're choosing a good material, especially the low K materials with a lower activation energy, then which will giving us a higher nonlinearity and higher immunity to suppress the steam path current. And this, besides of the experimental temperature and set CCL acceleration, we do some derivation for the current sweeping, current transport mechanism understanding. And by ruling out many different kind of transport mechanisms that we linking into the Paul-Frankel emissions that I will not go through the derivation in details, which you can, if you are interested, please find it out in the reference. But the key takeaway is that the nonlinearity, the self-selectivity is proportional to 1 over square root of K, which means that we need a one low K dielectric constant, one low K layer with a lower dielectric constant, and which will giving us a very good higher nonlinearity for the self-selective RRAM.
Hi.
And then,
So,
yes.
yes, so we
Oh, yeah.
I
Okay.
wanted to remind I wanted to remind the audience members that they can ask questions in the Q&A. We have a couple questions here. But before that, I wanted to kind of ask a more general question, which is this what's really nice about this talk is that you're really at the lowest level of the stack, the hardware, the real physics. What are the implications of this RAM device? I know you're going to talk about this a little bit later in the talk, but for computing and so on. For instance, this sneaky path current, how much does it affect, like, if you don't treat it, how much does it affect using the device for memory or memory arrays? And, like, what are the implications for, like, maybe ML applications where maybe there might be different tolerances of, like, if you lose a couple, like a lot of this community has done stuff with quantization or facts that neural networks don't necessarily have to get to 32-bit precision to you can
Right.
save energy. Is there any advantage to the sneaky path current that you could foresee?
Right. Thank you so much for the question. Yeah. So sneak path current will be the one of the main root cause that will bring up overall power consumptions, and that's the one. And how it will also causing the noisy the like the read and write arrow I just mentioned about, and there will be much more randomness into the weight storage in the neural network applications. And there's a two kind of studies saying that this noise can be helping us accuracy, and but there's supposed to be one optimized point that for the accuracy judgment, saying that does this noisy really helping with during the training or during the inference. So they're still under investigation, but that's an excellent question. Thank you for bringing that up. Yeah.
And now, two more specific questions from the audience. So, one attendee, and I'm going to kind of summarize it, is asking about the differences between MRAM and SRAM. So, maybe some competing memory technologies where MRAM feature sizes are much smaller than SRAM, though they're noting that in practice, when you look at memory data sheets, it seems like the embedded MRAM are more or less the same size as an SRAM. And this is, they quoted GF 22 nanometer technology. So I don't
Right.
know. This might be a very
Right.
specific question, but if you have some insight about
Sure.
different choices of memory and how their feature sizes might be smaller, but how does that actually end up into the array?
Sure. Thank you so much for the question. That's excellent question. So, footprints is definitely the downside for SRAM. So SRAM has required much more larger the footprint in the hardware, and MRAM has much more scalability. And but the cost for MRAM is high, and which is one company has just released the into the market for their products in January, and this is very promising result for that, and especially that's using for the AI chips. That's very exciting, and I would say MRAM has a very excellent stability and also the very small variability. And I would say MRAM still has some space to improve the multi-level adjustment because it has much more limited memory window for adjusting the multi-level cell applications. So that might be the one future path for the MRAM devices. So, yeah.
And then Krishna had a specific question of what is the threshold value for the low K for self-selector?
First of all, I didn't quite get the question. It's possibly mentioned about the dielectric constant number, or yeah,
Yeah,
I
the low
assume
K
that's the
dielectric.
question. Yeah.
Yeah.
So for silicon oxide, so we have been tested a lot of different kind of materials, and I would say the criteria for low K layer should be at least under the dielectric constant of 5. And beyond that, we didn't see any kind of self-selective behaviors, and which will be the obstacles to realize this kind of devices. Yeah.
Okay, great. Well, we'll continue on with the talk, but just as a reminder to the audience, please use the Q&A to keep asking more questions, and we'll have some time at the end of the talk. But we'll have Professor Chen continue.
Sure. Thank you so much. All right, so we talk about variation. Thank you for the variation questions. So, RRAM has been blamed on the issues for the device-to-device variation. And so we trying to come up a solution for that is, hey, if we see a lot of tail bits in the array, and we don't want to give up that array, and we don't want to using the ECC or buffer row for that, then is there any intrinsic method that we can use to solve those tail bits? And this is coming up as a, we call it a positive pulse treatment that we can using to recapture the filament and trying to bring that switching gap into the low K layer. So we're starting with the low K, we're starting with the lower nonlinearity tail bits, which is the blue cells in the schematics. And we're trying to solve that, those bits that we don't want to give it up. And this is the result that very exciting to us is that we trying to bring up the nonlinearity with the adjusting pulse height, pulse width, pulse number, and using the AC treatment, which is much gentle than the DC SWIP. And then as you can see that the result turns out good is that with adjusting the pulse height around the 2 to 2.2, then with a certain pulse number, then you will see that the nonlinearity can go up to 80, more than 80 in this kind of operation region. And not only that, we found out that without the DC set operation, we only using the AC pulse for the recapture process, then we further bring down the pulse height to below 2 volts, and then which will giving us much more low power and operations for that. So this is how we don't need to really give up the hardware tail bits, but there are still some ways that we can control from our external circuit that we can treat our devices to back to the functionality level. And some benchmark for this bilayer Selector-less RRAM devices. So as you can see that our work is in the high K and low K structures. And as you can see, it has a good memory window with the good nonlinearity, and the switching energy is lower. Is comparable, and then also the nonlinearity is good. So the switching energy for this kind of Selector-less RRAM is 40 picojoule per bit, and this is current benchmark. We are still doing much more work on how to optimize this and how to reduce the switching energy. So in terms of the application for neuromorphic computing, trying to using this kind of self-selective devices that we don't need a transistor on, is that we measure the long-term potentiation, long-term depression as the pulse number changing, and the conductance will change. So with this analog conductance change, we can utilize that as the primitive to store the weight during the training. And then we're using the MIST data set to realize that this kind of hardware devices can really do the training, and how was the accuracy. So the accuracy current records is by using this bilayer staking structures can be reached to 90% with certain epoch. And then compared to the conventional single layer RRAM, it's only 30% of the accuracy. So this is a preliminary result that we're using that self-selective devices trying to realize the neuromorphic computing, and also the power consumption can be low. So the right-hand side is also compare the LTP slope, LTD slope with the accuracy using the MIST data set. So there's a linear requirement for your LTP, LTD slope, and there are certain numbers will be giving you your optimized accuracy during the neuromorphic computing. So not only the memory devices, we talk about selector. So as you can see here, we're trying to realize the one single cells, but which can using as a selector and selector-less devices. So this is how by tuning the operation polarity, then you will see the different structures, different functionalities in terms of the left-hand side bigger will be the selector-less RRAM, and the right-hand side will be the selection devices. So this will simplify. This will be expected to simplify the circuit design and penalty for the using a lot of different components. And we wish this kind of dual functional RRAM can be realized to help with solving reducing the cost and solving the complexity in the fabrication. And I would like to move to the next topic. Is the newest topics and that we are working on. So one topic is called helical microstructures, that we're trying to further reduce that device area and trying to using the air gap in the helical structures, because air gap has the lowest K value. So we're trying to using that combined with the promising oxide layer, high K layer. Then we're trying to realize a good nonlinearity. I will not go into detail, but the concept here is that we're trying to using the air gap into the self-aligned microstructures to realize the selector-less helical-like RRAM. And this is ongoing project. And as you can see, by choosing the different kind of materials, then you will have a different power consumption for the selection devices. So the top is a higher power. The lower one is a forming free volatile switching that's still under development. And we are trying to using this one for the selection devices integrated with the helical structures, and trying to understand that how does this be able to integrate it for the high storage class memory by using the self-aligned process. And then this volatile switching can be bring back with the one refresh reset cycle. So this is still ongoing projects, but we do see some preliminary result, which is exciting to us. And then I would like to have some introduction about reprogrammable one-time programmable memory. And this is the technology that using this self-selector-less RRAM, we can also using this as a one-time programmable memory for security reason. And this study we studied a different kind of operation temperature, which will bring us a different kind of dielectric field state. I will not go to the detail, but I would like to mention is that by the self-selective RRAM devices, we can also using that for the fingerprint storage and also the security application. And in terms of backend offline compatibility, this is a ruthenium oxide-based that memory devices we're trying to build up, and the current security primitive using the dielectric fuse is mostly higher than 2 volt, and we are trying to using this ruthenium oxide, which has a very good immunity for the electron migration effects that we can integrate it in the backend offline emergent memory. And then this will be the target that we want to reduce this dielectric fusing voltage and current to very low power for the very low power consumption hardware security. Radiation effect is the topic we are studying on, is that we trying to understand the self-selector-less RRAM. How does that respond to the radiation effect, and targeting on the future in-space manufacturers, which can lean in on the microgravity enhanced electronics manufacturers. So this is also the ongoing projects that are happening in our group as well. And I want to show some like a very preliminary result, which is a time relaxation behaviors and compared to the radiation effect. So if you seeing this time relaxation with the radiation effect on the ruthenium and ruthenium oxide, you can see there is a split out current drift between those two. So the key takeaway is that the displacement current causing by the cobalt 60 gamma ray is suggested to increase the memory window. And we do see this memory window increase with the decrease the high resistance state current. And I will not go to detail at this moment due to the time constraint, but we will keep doing the different kind of radiation tests, with including the heavy ions, and trying to see does that affecting the inference and also the training accuracies after we do the pulse radiation. And then one topic is about the transparency of this kind of oxide RRAM devices, which is that we can using this ITO integrated with tungsten oxide structures to realize the transparent resistive random access memory, and this can be seen as the optical driven low power, ultra low power RRAM devices for the embedded memory devices applications. And this is a preliminary result. The key takeaway is it has a very ultra low switching voltage, which is below 1 volt. And in the planar switching devices, which has the length of around 10 micron to 100 micron. So this is exciting news that we can realize a very low power applications in these RRAM devices and with the acceptable memory windows. So one of my last topic is about the temperature effect during the training and inference process. So as we know that in neural network, the current study is focusing on the training, and there's consuming a lot of powers that each time if we want to do the training each time, then they will consume a lot of power during your storage wait, during your training process using these Synaptics devices. So my question to myself is that can we not using the training primitive every time, but we store the weight, and every time we're trying to do the inference, then we can retrieve the weight again. So this is how the temperature effect going to be important in this kind of operation. So this is a result that's saying that with the training under the different temperature, you see the accuracy has been shifted, and which is unwanted result that we don't want to have the accuracy shift with each time of the training. So this is also causing a power consumptions, even though you have a training accuracy can be improved in the under the higher temperature, but the power consumption will be increased with the training epoch. So we want to do the inference scheme right here, and how does that the temperature delta going to be affecting your training process? Is that we have a high resistance state and low resistance state, which has a different sensitivity, as you can see here, with a different temperature sensitivity of the operation. So the weight storage should be updated with the temperature sensitivity and with the post training. So basically, if you are stored the weight after the temperature operation, and then we want to see how does the inference accuracy being affected. The key takeaway is that the temperature delta increase or decrease will be affecting your inference accuracy, and which is causing by the overactivated and underactivated phenomena in your hardware primitive. So this is bring us the conclusion that we need to find something has a lower temperature insensitivity, which is temperature insensitivity. I'm sorry, which is the temperature insensitivity, and which has a lower response to the temperature and operation effect. So this is the study we collaborate with Intel for the last year IRPS publication. So if you're interested, please check it out. Okay, and then let me conclude my talk. And so in this talk, we talk about the hardware primitive for the selector-less RRAM devices with the bilayer staking structures, which has the self-rectifying behaviors, and also it has suppress the sneak pass current in the crossbar array, which can reduce the fabrication cost and complexity. And then it can be optimized with the set compliance current limit modulation. Activation energy can be using as an indicator for this resistive switching gap location optimized. And also it can realize the multi-level cell applications that we can using that for the ultra scalable crossbar array architecture. And then the synaptic behaviors of this self-selective RRAM resulting in 90% training accuracy in MINS data set. The temperature effect on training and inference on the RRAM primitive is investigated for the neural network applications. And then there's more devices we are looking for and new materials we are working on for ultra high low power or ultra high scalability RRAM devices for the next generation backend of line embedded memory devices. So with that, I would like to give my acknowledgement for the faculty member I collaborate with, the students and collaborations, and also industry sponsors. So thank you very much for listening.
Okay, great. Thank you. I'm going to start while people are thinking of a question to ask is, what was really interesting is the memory for synaptic, for neuromorphic computing. Like, it's clear that, like, as you go to these really low power emerging technologies, like, you're identifying temperature as a major maybe challenge to deal with. I guess, like, I'd like to hear a little bit more about like what are the challenges of the temperature, like you were mentioning for training or and inference both. What do you envision as like what do vertically stacked machine learning or AI applications that consider very low power memory? What are the things they really have to consider uh, to
Right.
allow this technology
Right.
to be useful for something like the tinyML applications the community
Right,
is interested in.
right. That's a great question. Thank you for bringing that out. So, for the, I would say in my perspective, I would say the power consumptions will be the key. So, if that's if it's so embedded memory is usually integrated in like a Metal 5, Metal 6, and above, and how to find a low power driver selection devices for realizing controlling the each time when you are doing a huge array of the training, then each time you need to have a precise control for your backend offline memory, and the power consumption could be expected as a very high, and that will be affect your accuracy and also your speed, right? So I think the power, the integration temperature, I mean the temperature for your overall integration process will be very important.
Do you think an AI or TinyML algorithm could be trained to handle these hardware
Interesting.
or
Yeah.
made more resilient to it? So maybe you don't have to there's a lot of engineering physics work to make these devices reliable, but could it work on imperfect RRAMs?
That's very interesting the comment. Thank you so much. Yes, I believe so. So uh, yeah, definitely. So for the there's a many in the manufacturer, there's definitely a lot of the machine learning needed for optimize the overall process and also post process. So when client receive the chips, can they do some refresh and also some recovering for overall the relaxation of the hardware is a very important topic. I agree with you.
Okay. Well, let me conclude here the talk. Again, the video is going to be posted online, and we can answer any questions. You can write questions in the forum, and we will answer them. We want to thank again the TinyML Talk strategic partners, particularly our executive strategic partners, ARM AI, Edge Impulse, Qualcomm AI Research, Sentient, and our platinum strategic partners, Deep Light, Klika Tech Global Solutions, Reality AI, Renesas, and our gold strategic partners, PhotoHub, Maxim Integrated, Latent AI, Microid AI, NXP, Seed, SensiML, ST Microelectronics, Synsense, and also thank our silver strategic partners listed here. Our next TinyML talk is Tuesday, April 12th. Professor Davis Tuya from École Polytechnique will talk about machine learning, supporting ecology, supporting machine learning. Webcast starts at 8 a.m. Pacific time. Thank you for attending, and we'll look forward to see you at the next TinyML event.